How does a human generate enough force to stop a man's heart from only 1 inch away? Using modern skeletal mapping, we are deconstructing the mechanics of Lee's strike to understand how micro-rotations and neurological timing create such a high-velocity mechanical impulse. In classical mechanics, generating terminal kinetic energy traditionally requires a sustained acceleration phase across a significant spatial distance. When that acceleration pathway is constrained to a single inch, the time available to build velocity is almost non-existent. Despite these constraints, Lee's execution of the strike is a documented physical anomaly that allows for a rigorous scientific deconstruction. The terminal force does not originate in the muscles of the arm. The impact is the result of a highly synchronized, full-body kinetic chain. This chain is managed by neurobiologically altered white matter, which functions as an advanced biological operating system for the body. Mapping this system requires us to look past the point of impact and analyze the entire biomechanical process from the ground to the brain. Biomechanical researcher Jessica Rose notes that the strike is a full-body action initiated at the lower extremities. The engine begins at the feet. Ground reaction forces at the ankle push off the floor, creating initial energy. An explosive knee extension breaks systemic inertia as the joint snaps straight, transferring energy upward and forcing the hips into a high-velocity rotation. Human biomechanics utilize what are known as torsion springs. The fascia and tendons across the core and shoulder girdle operate identically to these mechanical springs, storing energy through tension. As the hips twist, they wind these anatomical springs, capturing the rotational kinetic energy generated by the legs. When that stored energy is released, it jerks the thrusting shoulder forward with massive acceleration. By the time the arm begins its forward trajectory, the core and lower body have already converted ground forces into a massive reservoir of rotational energy. As the focus moves to the arm, we can observe a mechanism called sequential kinematic stacking. Energy from the shoulder travels down the arm like a cascading wave. The elbow extends suddenly, timed to trigger after the shoulder's forward peak. The final input is a micro-rotation, or flick, of the wrist just before the knuckles make contact. The velocity of this strike is a product of sequential peak acceleration. Terminal velocity reaches its maximum only because each joint hits its absolute peak acceleration at the exact millisecond the previous joint transfers its energy. Muscle fibers alone cannot achieve this level of microsecond synchronization. Raw muscle size is secondary to the coordination required to stack these peaks. The arm is essentially a calibrated conduit, compounding the kinetic energy generated by the body's engine, rather than creating it. At the moment of contact, the physics of the collision become the deciding factor. Instead of pushing through the target, Lee performs an instantaneous retraction. This action is explained by the impulse momentum theorem, represented by the formula F equals delta P over delta T. The rapid retraction drastically shortens the impact time. As that denominator shrinks, the force variable spikes. Compressing the energy transfer into a fraction of a second amplifies the peak force experienced by the target. In a standard strike, longer contact time dissipates the energy, resulting in a lower terminal shockwave. The 1-inch punch is an exploitation of impulse compression, maximizing the force by minimizing the collision's duration. Executing this chain requires timing that borders on the limits of human biology. Neuroscientist Ed Roberts conducted a study at Imperial College London to find the source of this short-range power. His research found that martial artists generate significantly more force than non-practitioners with identical muscle mass. The difference lies in the brain's hardware, specifically the supplementary motor cortex. This region is responsible for the coordination between the muscles of the limbs. Within this area, the microstructure of the white matter handles the communication between brain cells during high-speed motor recruitment. Through neuroplasticity, the brain physically rewires its structure to adapt to new demands. Decades of precise, repetitive practice forced Lee's brain to adapt, increasing the complexity of these cell connections. This split-screen comparison shows the difference in white matter density. The expert's brain has the physical infrastructure required to synchronize the body's movements with extreme accuracy. The overdeveloped white layer acts as the controller, managing the speed and sequence of the entire kinetic system. When the entire system operates in harmony, The biomechanical engine and the neurological controller function as one frictionless entity. The 1-inch punch is a masterclass in biomechanical engineering, made possible by an optimized neural operating system. Generating this level of kinetic output depends on more than just the expansion of muscle mass. It requires the precise calibration of physical space, time, and neural pathways. Lee's strike serves as a prompt for modern science to look past raw physical metrics and into the neuroscience of human coordination. Explore the mechanics that shape our reality. Click the subscribe button, activate the bell, and join us for the next scientific investigation on TEMBODocs.